In this video, I'm going to talk about states of matter. So this is really about the three states of matter: solid, liquid, and gas. And what we're going to be doing is learning how to describe on a molecular level what's happening with solids, liquids, and gas. We're going to be able to explain things that you already know to be true. So first thing I want to get out of the way is that scientists use a couple different words for this. They say states of matter, but we also say phases of matter, and those two mean the exact same thing. And there are several phases of matter out there. The ones that we're most familiar with are solid, liquid, and gas. There are other phases of matter. There's plasma, which happens in the sun. And then there's a fifth phase of matter that was just discovered a year or two ago. I even forget what it's called. There are supercritical fluids. There's Bose-Einstein condensates. So if you get into funky science, there's really actually many different states of matter, but the ones we'll focus on are the ones we're used to: solid, liquid, and gas. So let's take a look visually here. Here's a depiction of a solid, and if I hit play on this simulation, the first thing you'll notice is that the particles in a solid are in a nice, neat order, right? They're sitting in a spot. They have a place, and it makes this nice crystal lattice, and they just stay right there. On the other hand, you'll also notice that the particles are always moving. So this is kind of a first fact that you need to know about particles in any phase of matter, is that the particles never ever stop moving. Okay, so let's start with solids. Or let's do that fact. Particles in any phase are always moving. With a solid, as we just saw, those particles are just kind of vibrating in place. When things get hotter, maybe you know this from junior high, but in general, when things get hotter, the particles start moving faster. And conversely, if you make things colder, particles slow down. So the temperature at which particles stop moving that is 0 kelvins. Okay. And 0 kelvins is also called absolute zero. Now, absolute zero is a temperature that has never actually been achieved, and it is theorized that this temperature is impossible to achieve on Earth. We've come pretty close. There are movies you can watch about this, but absolute zero is a theoretical temperature where particle motion would stop. But in general, we can't reach it, and particles don't stop, even in a solid. Okay, let's switch to a liquid. Here's my liquid, and right away you'll notice that the particles are not in a nice, neat order. If I start the animation, you'll notice they're moving quite a lot faster. They're still quite close to each other, but they can move around. Okay. If I hit trace, you can see there's a trace in the background. It traces the movement of a random atom inside of there. That's showing where one atom is going. And you can see that that one atom can make its way around the container. With a gas, things are kind of similar, except they're spaced further apart. Particle motion is really, really fast. Collisions are really strong. Particles get around the container really fast. Okay, so these are kind of the differences between the three states. So we make this table, and this is something you're going to be responsible for knowing. I want you to copy this down. We're going to talk about the behavior of solids, liquids, and gases based on what we just saw in those drawings. So we've got 3 rows. And I want to talk about the shape. And I want to talk about the volume. Volume means size of each of these. So in a solid, when we look back at the solid, the shape of this whole solid is fixed. It's not changing. The particles are stuck in place. So solids have a fixed shape. Liquids, as you probably know, they have a flexible shape. Okay, the liquid will take on whatever shape is in the container. So flexible. Same with a gas. Whatever the shape of the container is, that's the shape of the gas. The size of a solid. Take a look back at the simulation. Is this whole chunk of solid getting bigger or smaller? No, it's not. The size of a solid is fixed. I'm going to skip down to gas. And you'll notice with gas, there's tons of space between the atoms. So if I were to make this container bigger, I can't do that on this simulation, but in your imagination, if I did that, you could imagine that these particles would be able to spread out further, and the gas can expand or compress. If I want to make the space smaller, the gases can just get closer together and keep bouncing around. So gases are the only state of matter that have a flexible volume, a flexible size. They can get bigger or smaller. Now a liquid, this one is the one spot that's a little bit tricky. The liquid has a fixed volume. And the reason for that is that the liquid particles, even though they can move around everywhere, they have to be touching each other. They're still bonded to each other. So that's kind of where we're going with this unit, is like, this is a fact that you're responsible for knowing all these things, but on a test I'm going to ask, well, why? Why do solids have a fixed shape, and why can't solids get bigger or smaller? Okay, so let's start with, let's do the volume. So this is example question 1. Why do solids have fixed shape and size? And the general format for answering these questions is to have a because. Okay, because. And you always want to talk about the particles, right? So if I give you a test question like this, always start your answer with because the particles. And in this case, you just talk about what the particles are doing or what they're not doing. So here's my solid. Because the particles are bonded to each other so strongly that they're stuck in place. Okay, the particles are stuck in place. Okay, due to strong bonds between them. So this basically explains both of these questions, right? If the particles are stuck in place, then the whole thing can't change shape, and it can't get any bigger or smaller, again, because the particles are stuck in place. So then I can ask a similar question, right? Why does a gas have a flexible shape? Why can a gas change a shape? Well, the particles can move anywhere they want. Same thing with a liquid. The particles can move anywhere they want, so a liquid has a flexible shape. Now what you should do as an exercise for yourself is you should answer this why question for all 6 of those boxes up in this table. Why do solids have a fixed shape? Why do they have a fixed volume? Why do liquids have a flexible shape, but they still have a fixed volume? They have the pass over there. So I'm going to throw that one in here. Why do liquids have flexible shape but fixed volume? And just like last time, we're going to start our answer with because the particles flexible shape If it has a flexible shape, that means that if I change the shape of this container, the liquid will change to meet that shape of a container. Well, that's just because the particles don't have to be stuck in place like they are in a solid, right? See these two atoms? They don't get to move around the container. But if I pick two atoms in here, they can move around the container. So the particles can move around. That explains why the shape is flexible. But why can't the liquid get bigger or smaller? But the particles must still touch each other. That's the reason why. And it all has to do with this bonding strength, right? In a solid, the bonds between particles are really strong. In a liquid, the bonds between particles are not as strong. So now it's still bonded together, but not so strongly that they're stuck in place. So the particles can move around. In a gas, the bonds between the particles are not very strong at all. The particles are moving so fast that they've broken those bonds and they can move everywhere. They can even move away from each other. Whereas in the liquid, they're still stuck to each other. So that's basically it for this. Look forward to the next video where we'll talk about phase changes, where solids change to liquids or gases or vice versa.